Hi everyone, welcome to our event. This event is brought to you by Datadog's Club, which is a community of people who love data. We have weekly events, and today is one of such events. If you want to find out more about the events we have, there is a link in the description. Go there, click on this link, and you'll see all the events we have in our pipeline. Then, very important, do not forget to subscribe to our YouTube channel. This way you will get notified to awesome videos, streams like we have today with Nikita. And last but not least, we have a great Slack community where you can hang out with other data enthusiasts. So check it out too. During today's presentation, you can ask any question you want, and should we cover these questions at the end, or you prefer interrupting?
Yeah, I mean, it's absolutely fine. I mean, of course, it depends on the number of questions, right? And,
Okay. So if there is one question that is on topic, it's okay for me to interrupt you.
Absolutely, it's great. I would love to make this interactive. Yeah.
Okay. So the usual intro from my side is over. Now, Nikita, the floor is yours. Let's start.
Okay, great. Then let me share my screen and at least ensure that everything is working. Yeah, at my side, yeah. So, yeah, I have to. Can you see my screen? Right, everything.
Yes.
Great. So let me position you as well. So yeah, I hope you will help me with questions. Yeah, and I would love to answer them during and maybe sometimes I will ask questions to the audience as well to add some.
Yeah, there is one thing to keep in mind is that there is a 30 seconds delay between when you ask the question and when the audience hears it.
Yeah.
So it's not super convenient. So if you ask a question, then we will need to keep talking for some time before we get to see the answers.
Yeah. I will ask rhetorical questions, which I could ask myself. And
okay.
Yeah, that's great. Okay, then let me first introduce myself. So I will present the talk, which I presented already 2 times. So yeah, I will share all the quote and presentations as well with the audience. But let me first introduce myself. So my name is Nikita.
Can you please maybe go to full screen?
Yeah, for sure.
Yeah, sorry.
So let me introduce myself. So my name is Nikita Iserson. I work in software engineering for around 10 years. So I worked as a web crawling data engineer. I worked as a data warehouse and enterprise integration data engineer. Worked in such companies like SIS Institute, SAP, Tigergraph, and S&P Global. So this talk is the accumulation of kind of 5+ years of experience I had working with different customers and use cases in the area of fraud detection, sometimes very conservative, right? Like major banks, sometimes more modern and innovative, like fintechs and e-commerce startups. But yeah, I will try to summarize the same issues everyone faces. So yeah, the talk is today about fraud detection with graph features and GNN. And yeah, feel free to follow myself at LinkedIn for sure, because I write almost every week some useful posts in the area of, explainability, fraud, recommender systems, graph neural networks for different industries, started from retail, telecom, and banking, going further to manufacturing, process analytics, and reinforcement learning. Okay, so let's start fraud detection with graph features and graph neural networks. So yeah, let's start first with some boring, maybe business slides, but yeah, fraud types continue to grow every year. So this is already a little bit outdated slide, right, from 2021. In 2022 and 23, we have the rise of many different types of fraud, mainly synthetic identity fraud, also authorized push payment fraud, mule fraud. So the global economy, which has all this current friction, like supply chain shocks, still some COVID programs, and cybersecurity, different conflicts spanned over the continent. So yeah, everything goes as a very good environment for different fraud to grow. So we have, of course, financial fraud in the center. We have insurance fraud, mainly fraud with claims. We have loan default fraud, when from the start you will not have any repayment for your loan. We have money laundering, which is a little bit different concept from fraud, but still, it refers to financial crime as well. We have fake account fraud and account sharing fraud, which sometimes leads to the change in stock prices of major tech companies. Transactional fraud, of course, is very popular. Credit card fraud, sometimes it's even friendly fraud when your friends and colleagues are using your credit card, or it may be card not present fraud when your card is accidentally used over the internet. It may be social engineering when fraudsters they steal your push payment authorization code and etc. They may do it with social engineering, and they may just do it over sniffing SMS channel, because actually SMS channel is very insecure, right? That's why most of the companies now introducing their own authentication tools, right? And we have also Bitcoin fraud and social network fraud. And sometimes it's really in terms of the social network, I cannot mention large language models and generative AI, which will of course be very useful for some projects, but that's very good in generative fake and synthetic content, fake reviews, fake posts, fake profiles, fake videos, and etc. So we've seen already some videos with Trump and Pope. Some photos. So of course, this requires much more robust and adaptive and dynamic pipelines to fight the fraud. It's very difficult to survive using, just a fixed set of rules implemented over some workflow engines. And sometimes, for example, misinformation or disinformation fraud may become really sophisticated. For example, we all use LinkedIn, as an platform, as a social media platform. But in one example, we faced with the case where the person was able to rise the number of the followers, from 7,000 to 70,000 just in 2 or 3 months, changing the identity. When you have some forest fires, the identity was changed to the firefighter with the nice photo, and posting the photos from the forest fighting with the fire. And then with the ship accident, that was the profile identity was changed to the ship crew. So as you see, there are lots of such things like fraud camouflage. So fraudsters try to connect their activities, and we some try to pretend that they are actually they have legitimate intents, and they try to connect to the usual entities and etc. So of course we have ad click fraud and duplicate ad fraud, etc. And account takeover, which when access to our account is stolen. From the technical perspective, of course, we have the graph in the title for the current talk. So what are some reasons to use graph methods? Not just graph neural networks, but as well graph features and graph algorithms for fraud detection. So the first issue, which you will probably be asked for, about if you go for the interview for fraud detection data scientist, the first issue you will ask about is, of course, class imbalance, label scarcity, and label fidelity. So in most production use cases, the percentage of fraud does not go higher than 1% of your whole database. So the number of labeled cases is very limited. They are rare events, and for different fraud typologies, you have again different labels. So by fraud typologies, I mean, for example, transactional fraud, synthetic identity fraud, account takeover, or authorized push payment fraud. And they, of course, need to generation of different features, which makes the life of fraud analysts and data scientists really complicated. I already mentioned fraud camouflage, so we need to be able to handle some kind of context and feature inconsistency. We need to understand that, the person could not change their sex or identity very frequently, you know, and some anomalous activity jumps could be also quite suspicious. And yeah, investigation and exploration is also quite useful way to use graph, because yeah, once you predicted that some particular sample is fraudulent, you of course, or you block the credit card, for example, you have some kind of some process. Yeah, for example, yeah, you initiate the real dispute. For example, you have a chargeback from the merchant and you would like to start, and the dispute is started. You need to actually investigate and understand what was the issue. Was it just a friendly fraud when, you know, the wife used the credit card, or yeah, it was really card not present fraud when the details of the card were stolen. And in this case, it's quite useful because yeah, you sit, of course, remotely in your office, and you need without looking in all the supporting documents, you need to understand how to connect the dots. So actually, investigation and exploration graph tools were used in the industry since early 20s. Yeah, they were popularized by Chris Westphal. Yeah, anomaly detection. Anomaly detection is also quite important because it's also an approach to fight with class imbalance, yeah, and label scarcity. So you could use different techniques, starting from simple, you know, isolation forests, going further to some denoising autoencoders, and etc. Graph embeddings. Graph embeddings are, of course, a very universal way to encode, you know, some structural information into the usable features. Of course, they may lack some explainability, but if we would like to have, you know, something almost anonymized, yeah, universal, and you would like to apply it to many use cases, many different fraud typologies, yeah, that's really a great way to encode your structured information, money transfers, or connection between entities. You could concatenate graph embeddings with natural language process embeddings and use it for the entity resolution and fuzzy search as well. And yeah, in this case, your graph may be almost everything. You may have natural graphs, like where the people send money to each other, for example, the money transfer graph, or cross-border payments graph. But you may have also indirect, implicit links and connections. For example, yeah, you may have, you may say that advertisements which were clicked by the same person or the same account are implicitly connected, or advertisements which were liked by the same account, viewed by the same account, or the session time was above some particular threshold. So yeah, you could really create very multimodal graphs and mine for some highly connected, isolated entities in there. Explainability and fairness. Yeah, this is also quite important because, yeah, with graph structure, graph connections and links, you could also augment everything what you are doing in the area of explainable AI. So yeah, you could create the models which will show you the context around your prediction. They will show, okay, not just which features contributed to the prediction, but also what was the context. For example, if you classify the account, they will show you, okay, this account was connected with this particular vehicle, with this particular claim, with this particular license plate number. If you talk about, you know, insurance claim fraud. So yeah, I mean, lots of top tech companies are using graph for fraud detection. So among them, Facebook, Amazon, Tencent, Alibaba, eBay. And yeah, in this presentation, I prepared a simple example of the graph fraud data model. This is kind of heterogeneous graph data model, which consists of, you know, usual entities like account or user, and user may have several countries, and user may be fraudster or not. So there may be the state of transaction, like failed or completed. There may be the type of, there is the type of transaction, which is like fee transfer or ATM withdrawal. Then also multiple currencies, or United States dollars. There is hour of transaction, like, you know, was it at night or during afternoon? And in the end, we create the very usual data mart for the fraud detection. it's not real in a way that, yeah, in real fraud data mart, there are usually much more features, maybe 200-300. But I try to make this diverse enough to represent many different types of features which could be used in this domain. So let's go through it quite quickly. We have features like first digit and last digit of the transaction. They could be quite useful due to the Benford law. So according to the Benford law, at least first digit of the transaction is distributed exponentially. So if you have like the most popular is 1, the second most popular is 2. So if you have sudden jumps in the popularity of some particular first digits like 9 or 5, it may be the case that some repetitive amounts are used for the fraud, for money laundering, to avoid some reporting threshold, because if you make some transaction like 999, it will not be above the reporting threshold, because, for example, all transactions up more than $10,000 in United States banks, they need to be investigated and reported somehow. They will build this. You look at them if you need to build suspicious activity report case. So yeah, and of course it's costly to use different structuring channels like mules, like Smurfs. And so that's why people may try to make transactions like 999 or 900. So and then we have usual counters and aggregation features like number of top-ups and average amount of top-ups. Let me explain what is top-up. So in this case, it will be about transactional fraud, which is top-up fraud. So it's a very simple case when the fraudster is using the stolen authorization code, for example, SMS code, to authorize the top-up to the credit card of the fraudster from your credit card. So if you suddenly see, okay, there is a transfer from your credit card and you didn't approve anything, so that may be the case. So we have the number of features like that, like number of top-ups, average amount of top-up, number of unique states, right? And by state we mean if it was failed, reverted, or completed. We have the country of the transaction, which is very important because there are, of course, some high-risk countries according to, for example, FAATF classification. There is also velocity of the transaction, and velocity is very important as well. In this case, it could be measured like mean time between the transaction, or average time between transactions. There is some, variation or deviation features like standard deviation of top-ups, and there are, of course, graph features like which represent usual graph clustering algorithm like Louvain community detection and page run. And there is also a feature which is called just an hour, because maybe you shouldn't usually do your transactions or ATM withdrawals at night, right? Or in some unusual location.
There's a question. Maybe if you can go back one slide here. So what kind of software do you use for creating this graph?
Yeah, and this particular screenshot is taken from the TigerGraph database. So TigerGraph is quite scalable database to manage graph.
Can you type it? I will put it in the channel, in the live chat.
Where do we have chat?
There is a chat, yeah. In Zoom, there should be chat.
Yeah. Okay, I see.
You type it and then I'll post it to live chat.
Yeah. This is the TigerGraph database. This is unfortunately, it's not open source, right? But probably it has some free trial cloud edition. Yeah, so feel free to check. Yeah, so this is not the actual graph, to be honest. This is the data model of the graph. In the same way, like data model could be created for the usual SQL database, and actually in the SQL database you could also create kind of graph-like schemas with the approaches like anchor modeling, or something like that. But that's another topic of discussion. So let me show how it may look like, the actual data. So if you go to exploration and investigation, so to be honest, lots of colleagues who start working with graph, they would like to first look at the whole graph, right? So in this particular case, we have, for the demo, I created just a small database of 1 million transactions, and I visualized that. But you probably understand that it's barely helpful for some actual work. So yeah, you may try to find some anomalies here, but of course, graph is multimodal, and you need to really score what do you think is the real anomaly. I think different embedding methods or manifold projection methods are used if you really want to find anomalies in a top-down approach. So there was such a company like Zindi, for example. They popularized topological data analysis approach to embed graphs in the low-dimensional manifold. Despite the fact it's really computationally intensive, there are other manifold learning techniques like t-SNE or UMAP or noise contrastive estimation, etc. But yeah, and practical cases, it's usually helpful to look at the graph in a bottom-up approach, right? So, for example, we have some account, another account. We see that this account has particular number of transactions reverted during his transaction in euros during early afternoon hours, for example, 5, 3, 4 p.m. And so we have another account who is doing his transaction during late afternoon hours, mainly card payments. Some of them were declined, and there is also a transaction like Great British Pounds, and we see what is similar between them. We see that both are doing fees, transfers. Some of the transactions are completed, and both are having, of course, some number of top-ups. So yeah, this is also done by the same tool, and of course, you could try to explore some multi-hop neighborhood once you find some suspicious pattern, and you could, of course, use it for your suspicious activity report to support your investigation. So yeah, that could be quite helpful. But yeah, in this particular talk, I will show you as well, the whole demo, which consists of the feature engineering let's actually switch to that maybe.
Before you do this, sorry, it took me a while to unmute myself. So there is a question about your previous slide.
Okay.
So here, maybe can you explain us a bit what are the edges and nodes here?
Yeah, this node is the account node, and this is the hour of transaction. Here, the brown one, we have the currency. This is the state of transaction, right? Reverted, completed, declined. This is the green one. I don't know, or does it look like blue? Is the type of transaction, like top up, transfer, fee. So it's like heterogeneous multimodal graph with different edge types, with different vertex types, but you still could explore,
Can we see if there was a transaction between these two accounts, that there was money transferred from one account to the other account?
Yeah, for sure. We could visualize this link as well in case we have money transfer.
So there is no link right now between these two accounts, but if there...
Yeah, exactly. Yeah.
I see.
In this particular example, because
if there was a transfer from one account to another, we would have a link with a different sort of edge between them, right?
Exactly. Yeah. But of course, only part of database is connected, because this is the database like from one bank, and they may transfer money. Usually they transfer money to another bank, and some accounts do not do transfers at all, for example, or just not active. So yeah, but of course, I have such example as well. But in this case, it's just not visualized. So yeah, let me switch to the demo. So yeah, we had this fraud detection with
There was a question about open source alternatives to this Tiger graph. I guess this is what you are going to show us right now, right?
No, I will show the only open source code. I will not show. It was just a visualization I found useful for the presentation, but everything which I will show is implemented via open source tools. So no.
Can you make it a bit larger, please?
Yeah, absolutely.
Maybe hit Control plus a few times. It's already very large. Okay. For you. Yeah, that's great. So now on my screen, I have a small screen. It looks readable.
Yeah. Okay. Yeah. So yeah, I mean, I will not go into every little detail of the code because I will share it after the presentation. Of course, we load some files about users, transactions, and fraudsters. And then we add functions to calculate some useful features, for example, like date features, right? And to calculate and evaluate model metrics. So yeah, this is then example of us calculating these particular features like first digit, last digit, some aggregates. And I think this is just the usual pandas operations, right? Where we first group something, then map it back to the original data set. I don't think that's really that interesting. The first thing which becomes really interesting is calculating the graph features. So we take very simple library, scikit network, which I think it's not for production use, but for the simple example, it works really well. So yeah, and we could visualize, we built our communities on a bipartite graph of account and transaction. So this is kind of visualization of user side, account side, and transaction side communities. So we see really large account communities, and this is done by bipartite Louvain algorithm. So Louvain algorithm is very scalable algorithm. It has n log n complexity, so it could be applied with 100 millions, 500 millions data sets quite easily. It's a greedy algorithm, so it's not precise. There are some improvements over that called I forgot. Yeah, I will follow up on that later. So yeah, we could then add these community features to the transaction. So yeah, we could also use some other graph algorithms to calculate communities like label propagation. Leiden, the better version of the Louvain algorithm called Leiden. So it somehow people believe that it creates more interconnected communities, but you should really check what works for you better. So yeah, we create communities with the label propagation. And in this case, we could see some other communities created in the same bipartite graph. So then we add these features to the data set again, and then we train two models. We train the model with graph features and without graph features, right? This is some exploration, right? For example, we could look at the exploration charts, like what is the percentage of fraud by the first digit. And we see that the digit 5 has really large percentage of fraud, right? And maybe digit 2, that's the first digit of transaction. We could look also at the graph features, right? Oh, for example, this is the chart for the country. Oh, no, unique states. This is the chart for the country. So we see that some countries are really fraudulent.
There are a lot of questions about the notebook. So as I understood, you will give us the notebook later.
Absolutely, yeah. Without the data, of course.
Don't worry, you will get access to the notebook, and then you will get to play with this notebook later.
Yeah, this is the different communities. So you see some communities are really fraudulent as well. Of course, it could be correlated with other attributes, right? But
there is a question like how these charts are useful. How are we going to use them?
This is just for exploratory data analysis. We look at our features, and overall, we would like to understand, do they have any information? Is there any, entropy in what we are trying to use as an explanatory features? And of course, if we see that some particular values show larger percentage of fraud, some particular values show lower percentage of fraud, we expect this feature to be informative.
So then, like when we use machine learning, then it will probably use these features. And then it means that we can actually use machine learning for detecting fraud.
Absolutely, yeah. This is just, to justify for your business user, maybe for the fraud analyst who is just using rules, and business knowledge, to justify that graph features may be actually useful. And some features like, first digit, last digit, you just show that, okay, there is correlation. We could use this correlation, and we need to investigate if this correlation is actually causal pattern, right? And so then we could check target statistics, right? We see that the percentage of the target is really, really small. It's less than 1%. For both train and test data set, we use group shuffle split to split it by the user ID. So in the test part of the data set, we will have only unseen users. It's not, there is no leakage Yeah, so we are doing that. And then we train just simple XGBoost classifier with almost standard parameters, right? And then I'm able to show you the feature importances. So let me make it a little bit smaller. And yeah, then we see that the Louvain community feature really it's coming on top. Yeah, we have also usual features like second, third, and fourth, like country and aggregates, but we have also label propagation community as a fifth most important feature. So we have then velocity, last digits, and other aggregates. So just to show you the integrated impact of that, I created also kind of model evaluation example. It's not the usual model evaluation example, it's kind of financial model evaluation example. Why? Because we model the revenue per every true positive example. So we say, okay, what is the revenue which we could recover from every true positive prediction? And in this case, it's about $1,000. And then we model what is the costs which we bear in case of the false positive. So false positive means we need to check the transaction or we need to unlock already blocked transaction. So according to our calculation, of course, it's an approximation, right? We need around $600 to unlock for all this investigation process, which is going through the dispute, right? When credit card is locked. And we need some money also, we need to bear some cost to check the transaction as well without locking it. And then we create the split between by the score cutoff. So why I think it's important, because in production, I hear sometimes people are trying to compare like, okay, what is your F1 score, or what is your precision and recall, right? What is your percentage of false positive? What I wanted to explain here that these are point-wise metrics, like, right? So precision and recall is measured only on particular threshold and F1 score as well. F1 score weights true positive, false positive and false negative in a equal way, right? And sometimes it's important to add the revenue and cost weighting. So here we have the table where we split the data by the prediction cutoff. We calculate how many predicted accounts we have, how many correct predictions we have, how many incorrect predictions. Then we calculate precision recall for every threshold, but we also calculate the revenue from the correct predictions and cost from incorrect prediction, cost from false positive and false negative, and revenue from true positive. And then we could basically visualize the chart and look for the optimum point to find the optimal threshold in a kind of margin driven way. So this is the good example, because sometimes you see what is the money impact, what is the financial impact of the model, right? And we show that, okay, this could be the model with graph features, this could be the model without graph features, and yeah, or this is the model trained with some neural network. So we could really justify if we should move it into production if we have some approximation around financial impact. I will move to the presentation.
Yeah, there is quite a few questions about the notebook. Maybe we can cover them quickly. So the first question is, did you do any balancing? Did you?
Yeah, for sure. Yeah, let's go quickly to that. So the balancing is done simply via scale pos weight parameter. Mm-hmm. So in my experience, that's the best way to deal with imbalance. So lots of people are talking about, how it's called, imbalanced, oversampling, undersampling. In my experience, it rarely works. So either you go for an anomaly detection approach, or you just use balanced objective directly. So oversampling and undersampling rarely works in my experience, and is rarely done properly in terms of cross validation without leakage, right? Mm-hmm. More questions? Right?
Yeah, about cross validation. Why exactly you used group split instead of usual split?
Yeah, because I needed to ensure that the same users are not in the train and test. I needed to train only because one user may have. I build a model on the transactional level, so I classify the transaction because this is what needed for the actual inference. Lots of data sets around fraud detection, they classify the user but classifying the user, if your user is already classified, what you should do then, you need to classify the transaction and take the decision about the transaction based on previous user activities. So you need to train on users, and you need to predict for the new users, because if you will have the transactions from the same user in the train and validation, you may of course overfit.
Leakage, right?
Yeah.
Mm-hmm. Okay, and there is also a question, I don't know how on topic it is, if we can do any causal inference here right now, or it's simply about predicting.
Yeah, I mean, I plan just tomorrow to publish a post about different explainability methods for fraud. There is a loose connection between explainability and causality. It still exists, right? To do this kind of causality, you need, of course, experiment, or you could do it based on experimental data, based on observation, or based on your domain knowledge. So if you take these correlations produced by the model and then go back to the graph data model and try to investigate and look at the neighborhoods, utilizing your domain knowledge, of course, that will be kind of causal inference to some extent. But you could also create A/B testing experiments, right? You could say, okay, we will implement these graph features to classify fraudulent transaction for some segment of our database, and you could actually measure the financial impact in the same way it's done, in personalization. You could, and it's even better to do so, because this way you will avoid the issues like, model, everything was discussed in MLOps, like concept drift, model drift, covariance shift. You will be able to understand if your model is robust enough but I will cover that later during the presentation as well, how to make the explainable and, robust models.
See the rest of the presentation.
Yeah. So it looks very simple, right? But because it's store example, yeah. But what are some production challenges which you may invest even time to build tools around things which I will tell now, because there are not many tools which exist on the market to cover that. So actually, if you talk about graph features, you need to think not about the static graph features, but about temporal graph features. Some important practical tips. Of course, you need to calculate graph features only on the train subgraph. For example, if you calculate the page rank, it sends the messages during the message passing phase across the neighbors, right? And if you would like to avoid leakage, you need to take the temporal snapshot of your subgraph before the inference date. That's why you will not look into the future during the page rank calculation. And the same goes about different features which you may have. For example, some approaches utilize k-hop distances to the fraudulent labels. For example, we could calculate what is the distance from the current transaction to the nearest fraudulent label, like 2 hops, 3 hops, 5 hops. You also need to calculate it only using train labels. You cannot look into the future, say, okay, in the future, this transaction is very close to the fraudulent label, because this will be leakage as well. You need to use time-based split, right, to see, fair model performance and how it deteriorates with the new users, new types of transactions, etc. So yeah, what I wanted to refer here. So there are a couple of tools. For example, there is temporal PageRank, right? There is temporal PageRank, which was developed. The implementation was developed by the Amazon colleagues, which could update PageRank values for the new node in an inductive fashion without recalculating the whole PageRank on the whole graph. There is also dynamic community detection algorithms like Louvain, for example, as well, which could work on the graph snapshots. For example, initially you calculate the community structure for the whole graph, and when new nodes and edges are coming, you could repartition them and assign them to the communities, or even create new communities. Yeah, and the usual inference process for the graph neural network, right? It looks like that. So you calculate online graph feature, you get the new account or transaction. You calculate online graph features using temporal page rank, or you dynamically assign this node to a community. And in parallel, you add offline features, like all these aggregates which I mentioned, like counts, maximum, averages, etc. And you could do it with stream table join, or you could do it as a stream join. It doesn't mean it's like real stream, it's mini batch fashion, of course. You could do it with Kafka or with Flink, right? You go to some persistency layer, you take together offline features and online features, and then you send it to an inference service to do a prediction. And of course, in case of the GNN, yeah, I'm already going a little bit
There is a question, is like, it seems that the graph needs to be updated every time you have an event. It seems very expensive, and I think you just covered that, right? You use all these things like Flink, the rest of the things you mentioned for exactly this reason.
Yeah, exactly. This is the reason, because you cannot update the whole graph every time you make the prediction. You just update it incrementally and periodically, maybe one time per day, for example, or one time per hour. You could rerun the whole algorithm to reduce the gap between the heuristical nature of the greedy algorithms, because of course it's approximate when you calculate it in incremental fashion. Yeah, okay. Yeah, impact of graph features. I also wanted to show this kind of chart. This is maybe less, more popular and more clear for most data scientists. So this is an impact of graph features on the model. We could see the precision recall curve, and we see, yeah, even with such a toy example, there is the real gap between the precision recall curve. So at least this way we could try to justify there is an integrated impact. It's not just, graph features adding some random noise and making the model to perform better. Yeah, we see that model with graph features performs better on the all sets of different thresholds in terms of precision and recall. Yeah, I had also part about explainable fraud detection, right? But I think I will cover it only quickly, because it will be a question actually to the audience. What do you use for the explainable fraud detection? And due to the delay, the answer will go immediately. I think most examples will be like Sharp, right? Sharp and Lime. And so despite the fact Sharp is quite good for the fairness, and it's just very black box permutation importance method, it could be really difficult to scale it to understand interaction features. By interaction features, I mean really how to extract useful interaction. And this is what is needed for the fraud analysts and fraud, business people. They look for different rules, right, which could have high precision and high recall, high coverage of the database, and, high percentage of prediction. And they're always curious to get these rules and try to investigate the causality behind them. Because if you have a rule which separately you have the low percentage of fraud, but collectively, like for example, this channel together with this device, together with this number of clicks, together with this social network community, brings you to monotonically increasing percentage of fraud, it's of course very interesting, because you see kind of complex pattern where you could try to connect the dots and improve the process. Because some processes are complicated to be improved, right, if you don't understand the whole semantics. So most of the people say they use Sharp, but at the same time Sharp really has low scalability in terms of interactions mining. So if you take any implementation or example, then for feature interaction, it's usually using like 5% or 10% sample of the database. And my experience shows that it's very useful to use the library which is called XGBFIR. It's the library developed by Matthias Müller, Kaggle Grandmaster. He's also from Berlin, by the way. He works at H2O AI. So this library is doing very simple thing. It just analyzes the trained XGBoost model and that extract useful interactions from that. So what we could actually do, we could train XGBoost model, and then we could use this library to extract useful interactions and add them as a features back to the original data set. So we could enrich our data set with XGBoost semantics. And this way, we could even get the same quality like XGBoost using logistic regression model. And of course, logistic regression model is even, much more simpler for the production use case because of the fast and parallel inference, which could be implemented, using any platform. And that's very important because once you go into graph neural network world, graph neural network are not that matured at this point to automatically handle feature interactions. It's important to note that unlike other deep learning methods, graph neural networks, they still require not features to be trained. And these not features, if they do not contain feature interactions, you will lose this information. But augmenting usual features with the feature interaction, you could actually train graph neural networks preserving XGBoost or gradient boosting semantics, which is really useful. Then I had simple introduction slides about graph neural networks, right? That we train graph neural networks on the graph, and then we classify and label it nodes. But this is just an example.
Tell us a bit more about this, like what exactly was happening here.
We have some transaction database, right?
The graph construction is this is what you showed us in
So because usual projection data sets, they're very large, we cannot train graph neural networks on the whole graph. So we need to use sampling, mini batch sampling. So we usually sample the subgraph. And there are lots of different sampling methods, which I've shown here as well, like cluster GCN, GraphSaint, Seal, or Grail, which preserve the neighborhood structure. So once we obtained the sample from the database, we have the labels for every node, and we could train it so we could use the graph neural networks encoder. So basically it takes as an input adjacency metrics and use convolutional layers in almost the same way like it's done for the computer vision network. So it's trying to use convolution to convolve the features from the neighbors, and it's trying to do message passing to then apply nonlinear transformation on the message passing steps. So first you aggregate the features of the neighbors, right, using the convolution, and then you apply some nonlinear transformation, and you do that multiple times. This is called message passing. So actually, message passing and graph neural network training, this is done kind of using graph itself as a structure to train, right? So the message passing, so gradient flow is going over the graph itself. It's the good thing from one perspective because it adds some, inductive bias to the problem, right? According to the graph structure. From another perspective, it could be bad because you may run into some over-smoothing or over-smoothing or over-squashing problems. But that's already some advanced concepts. I just wanted to show you some performance from the graph neural network model from the same example. So all you usually need to do, what is different in training graph neural network models to the usual neural network is that you need to define neighbor loader. So this neighbor loader is defined using TGML, Tiger Graph Machine Learning Library, right? But it's almost the same signature how neighbor loader is defined in PyTorch geometric, in Deep Graph Library, in Stellar Graph, etc. So you define your mini batch, and then you have the same, training process, and you have the performance. So in this particular case, we were able to, with some hyperparameter tuning, we were able to reach the area under precision recall curve of 50%. When in the case with graph features, it was between 30 and 40%. So even with such a huge class imbalance, like less than 1% positive cases, it was possible to build better neural network model. And of course, neural network models.
Just a question about this this code. So you used the same data set as you used in the previous demo. What is different between these two cases? Like, I guess here you don't need to do explicit feature engineering like you did with XGBoost.
No, you still need to do feature engineering because in the graph neural network case, you still have your features and they are assigned to the nodes. And that's why I find the graph neural network space that interesting, right? Because all the other areas like natural language processing and computer vision are oversaturated with architectures. You don't need to apply some domain knowledge, but it's a popular belief that graph neural networks, they also could encode just structure, right? If you look at any benchmark or any scientific paper, they of course try to use most information from the structure and typology, but even in molecular modeling, they still use, some features of the nodes itself. So it's still not possible. Sometimes it is resorted back to some kind of positional encoding. For example, you could take a centrality and say, this is your positional encoding, similar to transformers. Or you could say, you could take geodesic metrics, adjacency metrics between, some neighborhood, and you could say this is positional encoding, but still features are necessary for graph neural networks here.
I see.
Also, quite a useful thing is explainability. Some people say that neural networks, especially graph neural networks, may be less explainable. I put here some explainability examples from the another data sets, from the phishing fraud, calculated over the Ethereum data set. So to show different phishing patterns, when, some fraud account moving some money from legitimate accounts. So you could actually see the structural or topology patterns, and you could understand the explanation. So in this particular case, this is simple phishing fraud, and here it's kind of fraud camouflage when all the money are transferred to kind of legitimate account, and then in one go they move to a fraudulent account. You have also more complex patterns when you have like the fraud ring, like or even high velocity fraud when involves maybe hundreds or thousands accounts. So yeah, this is an example of explainability, and yeah, we have two notebooks for that as well. We have the notebook for explainable fraud detection, which I mentioned already. So I show how to parse gradient boosting model with the XGBFIR library, right? So I just show how to extract these interactions from gradient boosting. So first we train gradient boosting model, and then we extract interactions from that. And then we train logistic regression model with the same quality. If you look at the area under ROC curve, it will be 91%. And then we train logistic regression, and the quality is even better, 96%. It's better than XGBoost because we just use XGBoost features. And this is how these XGBoost features look like. So these are actually rules like user top-ups between 43 and 43.01, for example, or user top-ups between 23.5 and 24.5. And we have also the similar rules for the graph features, like label propagation community between 32 and 33. It means actually the 32 is quite risky. We have the country features, and we have more complex rules, like the rules of the two variables, like here, for example, top-ups, standard deviation is here, is between one set of values, and a number of unique states is between other sets of values. But of course, we may have some overfitting here, so we need to control it with the proper cross-validation. And the last bit, this of course fraud detection with graph neural networks. This is also part of the demo, but I think we don't have much time left, so I will leave it to you. You could look at the neighbor law there. You could look at the usual training loop, right? Normalize features, send gradients, calculate different metrics, and you could investigate different metrics here and how they grow over the training, and you could look at the some explanations as well. So yeah, I think this is everything from my side.
So chance you can share the notebooks right now with us?
Yeah. Of course.
I think for people it would be inconvenient to come back later to check.
Yeah. Okay.
So maybe you just
I will stop sharing then, right?
Yeah. Maybe you can just send to chat and then I will post this
Yeah, I will
the
do.
description.
Do we
So
still have
it
some
will be
questions?
in the description. Yeah, we have a few questions. But I think notebooks are more important than questions.
Oh, okay. 1 second.
Because like people ask, hey, we want notebooks.
Okay, that's great. Yeah, feel free to subscribe to actually my profile at LinkedIn, because I publish some notebooks for sometimes my notebooks, sometimes notebooks which I highly recommend. Just tomorrow I plan to publish something about explainable fraud detection. So I think this link should work, but yeah, let me know. Let me try it via incognito window, because of course I'm logged in. Oh, no, this is not the whole folder, right? This is just
Okay.
one notebook. This is just one notebook, but I wanted to actually share the whole folder. Yeah, feel free to ask more questions if
I guess
you.
it takes more time to share the.
Yeah, I found. Yeah, because there are two buttons you could actually share. You could actually share the notebooks, and you could actually share the folder itself.
So I see that there are a lot of thank you messages. Like this is awesome. Thank you. Thanks. Nice. Really nice analysis. Thank you. Nice talk. Thank you. So yeah,
Okay,
indeed.
thank you very much. Thank you very much. I'm checking the link with the incognito window, and it works. You are able to see
Sent.
everything. So yeah, let me send it now.
Unfortunately, we will not have time for many questions.
Yeah,
Maybe I'll just take the one from Slido. So a question from Hugo. I have a question about scalability. Given a system to detect fraud, it should be online in real time. Can these neural networks, graph neural networks, generate features for large volume of inputs? Like, can they work in real time, or it's still not there, and we need to use, these linear models or XGBoost for this?
There are lots of activities to make it work really in production. Yeah, of course, for less conservative institutions, financial institutions, still good to go to implement even gradient boosting models. But for fintechs and e-commerce companies, it's really good. If you look at the Alibaba, for example, yeah, they have lots of examples of using GNN in this quantization and distillation. It could be used in real time in production. The most problematic thing is that you need to sample the subgraph during the inference. And it's kind of not easy, because you cannot prepare the sample beforehand, because the sample could be associated with the new transaction or new account. So you could partition, you can only partition the graph, but you cannot prepare the sample itself. So you need to do a sampling in real time. And the problem that sampling really deteriorate accuracy. So if you take a smaller sample, then the accuracy goes down. If you take larger sample, then you need more time to access your persistency or access your cache. And in this case, what is done that you usually just parallelize it in a kind of voting or blending approach. So you have several threads, several inference threads, where you sample the subgraph, different subgraph multiple times, of course with some random initialization, and you make a prediction for every sampled subgraph, and then you average the predictions. And of course, there are some ideas how you could use hardware acceleration, starting from GPUs, going forward to FPGA to parallelize graph neural networks calculation. Yet graph neural networks are not that efficiently parallelized, because it's not just about matrix algebra, it's also about the topology of the graph, right? It's not really parallel in the way that you need to use some partitioning. But in production, you could go for some partitioning. So you could partition your graph beforehand with such things like influence-based mini batching. So this will be linear. This is just one of the maybe 1 year old, maybe half year old paper, influence based mini batching, and the name of partitioning algorithm. Yeah, I forgot the name.
Yeah, you can send us later. So there are also questions about the data that was used for the notebook. So maybe if you can later add the data to the folder that you already shared, that would be useful. Add instructions how to get the data.
No, I mean, not this time.
Not
To
this
be
time?
honest, yeah, but I will be happy to help everyone who would like to adopt the code for his own data, right? Because I think, for example, I could recommend you to use Zindi, Zindi fraud detection challenge, right? Which has the public data, and you could basically transform it into the same structure, because there is some very unique attributes which are used, just user account transaction graph, some aggregates, and graph features. That's
I
that.
everything to the description. So for those who are watching right now, so the folder with all the notebooks is there in the description, and also this time the name of the Zindi fraud challenge is also there.
Yeah.
I think that's all we have time for now. Thanks a lot. Sorry that we did not have time to answer all the million questions that you had.
I will be able to answer them via private conversation via the LinkedIn, so feel free to connect.
The best way to follow up is to connect with you on LinkedIn and then ask the questions there.
Just send a message there, because
And yeah, thanks a lot for joining us today. Thanks a lot for.
Thanks, Alexei. It was a pleasure to talk for your community.
Unfortunately,
Good luck.
Only 1 hour.
No problem. No problem. It's great.
Was
and
very
questions were great.
Very informative. So thanks again, and thanks everyone for joining us today.
Thanks a lot. Have a great rest of your day. Bye-bye. Bye.